a callback to much earlier in the semester. What's the difference between discrete and continuous data?
Is pre-displayed. How will we define a for this can be measured in high.
And it's really that idea of measurement. When I think of a continuous idea, I think about a whole range of options. We can go as fine as we want. And in discrete, there are fixed particular increments, whatever they are. They could be tenths, they could be units, but there are finite numbers about them. Continuity means that sort of smears out. So I want to think of this primarily as measurements: height, weight, uh, size, all sorts of things that I don't tend to think distances. I don't tend to think of them as having finite arbitrary categories. In which case, I have an idea, an interesting question here. If I think of a measurement, I mean, when I flip a coin, there are two options. It's either going to land heads up or tails up. But if I throw the coin down the length of the room, how far does it go? That's a measurement. It can go anywhere from 0 to the distance of the wall, and I could measure that as precisely as I want. What is the chance that when I toss this coin, it will be exactly 3 feet from this wall? Exactly 3 feet. Since I can measure as fine as I want, it's going to be really hard to be exactly 3 feet, right? It could be, 2 foot 11 and 7/8 to 3 foot 0 inches and 1/8 of an inch. So it depends on how fine my measurement goes. In a continuous idea, the probability of getting an exact value is 0. Because really, the chance it's going to be exactly 3 feet, I'd have to measure very, very precisely, wouldn't I? So it's really not reasonable to think about this. And since when we were thinking about our discrete probabilities, that was how we figured it out, right? Chance of it being the coin landing on heads twice or on heads 3 times, right? I actually counted exactly equals to. But in a continuous idea, we're better off considering ranges. What is the chance of being between two numbers? So if I said, what's the chance of being between 2 foot 11 inch and 3 foot 1 inch? That'd give me a boundary, right? And then I could have a whole range of possible measurements. So instead of thinking about specific particular values, I think about ranges of values. And for continuous ideas, this is a better choice. The unfortunate side of this is that continuous ideas are the basis for calculus. And instead of counting our sample space and counting our probabilities and doing those combination formulas like we did for the binomial, I now have to start doing calculus. No, I'm not going to do calculus in this course. We will have calculus done for us. I'm just going to take the ideas and then I'm going to cheat. Somebody else will have done the calculus for me. But the idea now becomes the important thing. I still want to use a probability distribution function. I still want to use a cumulative distribution function. So my idea for a PDF and a CDF should carry over. But instead of counting specific things, looking at a histogram, I'm going to look at a graph. So I can draw a graph and try and figure out what's going on with my PDF that way. So something like this picture. What I've got on the left here is a PDF. This is a person driving on a road on the freeway, and I want to know what's their speed. Well, the speed limit on this particular stretch of highway is 75. There's a lot of people doing around 75. The chance of doing 75 is pretty high. But exactly 75? Can you pin your speedometer at 75.0000 miles an hour? My cruise control isn't that good. Some people are really hauling this, and some people are slowpokes. But here's my distribution. And then I've got a cumulative distribution. Wait a minute. What did cumulative measure again? It measured up to a particular value, right? So in this picture, the y values here are adding up from this side, all of the y values before it. I beg your pardon? How the hell do you add up all of those little y values? Well, what you're really doing is you're taking the area under this curve. In calculus terms, this is an integral. It's measuring the area under. So when I think of being between A and B, I think of the area in my picture. I'm going to draw pictures like this a lot. Because that's the idea. I want to measure these areas. And as long as I know what my picture looks like, I'll be able to tell you what the area means. Now that means that all of the ideas we had about discrete probability distributions still apply. But now I want to make them apply to functions. So if I want to think about a function, I need this function to represent a probability. Now, this is where this change in phrase comes from. Instead of talking about these as probability distribution functions, we almost always talk about probability density functions when thinking about continuous ideas. This is where the switch in the language takes place. I need two conditions. Let's think about the probabilities we had before. There were two rules when I started talking about probability back in chapter 5. The probability of every event had to be between what two numbers? Aha. Which means my function should always have values between 0 and 1. Means it's always got to be bigger than or equal to 0. But then there was another rule about all the probabilities. When I looked at all the probabilities together, what did I get for all the probabilities? I got 100%, 1. So that means that the total area under the curve, going as far to the left as you want, as far to the right as you want, should be 1. Now, under in this case, the reason I put it in quotes is we really think about the area between the x-axis and the graph. Because I know the graph is bigger than or equal to 0, should be up here somewhere. So I think of under it, but I only go down to the x-axis. Whatever the picture looks like, all of this area should add up to 1. No matter how far left or how far right we go. Which means if I think about stuff that could be negative or positive, I might actually have to keep going all the way down to minus infinity. I might have to keep going all the way to positive infinity. It is not frequent that real situations spend a lot of time worried out there at the really huge numbers. But there are places where thinking about going out to infinity in either direction matters. If I think of this in calculus terms, this symbol, this elongated S symbol, represents the area under a curve. The curve F measured against the X, that's what the dx is for. And then the lower and upper infinity says all the way to the left, all the way to the right. You will never, ever again have to see this symbol after today. But with this idea in mind, all of the things we were doing become areas in pictures. Even mean, average, expected value, and standard deviation and variance. They become ideas based here. We had our expected value formula. Our expected value formula, which was the same as our average, what was that last chapter for the discrete behavior? What did I say to do to find the average? I took each value and I multiplied it by the probability, and then I added them all up, right? So I'm adding up each value times the probability of being that value for however many I got. Well, if I want to do this in a calculus term, this is the area part. That's the probability part. All I have to do is stick an extra x in. Well, wait a minute. We call this F, not P. So this says you're going to multiply the probability by the x, and then you're going to add up all the area. That's the same formula, discrete versus continuous. The same thing is true about my expected value and my variance. So I don't actually have to do anything differently in terms of the idea. I'm going to take x times the probability, and I'm going to add it all up. The way I add is now a calculus way as opposed to an algebra way. We're not going to do the calculus, but I want you to know everything we do is the same idea translated. All right, wait a minute. Page 235. Flight 202 is departing LA. I just want to identify which of these are discrete, which of these are continuous. Number of airline passengers traveling with children aged under age 3. Is that discrete or continuous? Because it's a count, right? 0, 1, 2, 17, however many. Proportion of passengers traveling without checked luggage. Why? Which means it's a fraction of some type, and I could measure it as far as I want. If there are 7 passengers and one of them is traveling without checked luggage, that's 1/7, right? But as a decimal, that's 0.142857, 14285. It repeats. Oh, crud. Okay. Weight of a randomly chosen passenger. And then depending on where I choose to round, if I say measure that weight in kilograms to the nearest kilogram, then it becomes discrete, but it could be continuous because I can measure as far as I want. Perfect. Let me think about the functions. What do the functions look like that go into this idea? I would like to know whether or not the following function is acceptable as a PDF. This function is defined in 2 pieces. It's got the value 0.25 from 0 to 1. Everywhere else it's equal to 0. If I ask you to graph this function, please notice I do not have a calculator or graphing device out. Let me think about what would the graph of this look like. If I just said the function was equal to 0.25 everywhere, what's that graph? Y equals 0.25.
It's just straight.
Technically, all lines are straight, but what's the characteristic you're looking for here?
Yeah, that's no.
There's no angle here, right? It's a horizontal line. Okay, but I only want that horizontal line from 0 to 1. So really, the graph of this function looks like this. At a height of 0.25. Just for that piece, and everywhere else it's equal to 0. Now, if I was really being a pain in the ass, I would say you'll notice it's equal to 0.25 at 0, so there should be a little open circle here. And it's equal to 0.25 at 1, so there should be a little open circle here. I don't care. I'm not going to be that precise about it. But the math teacher in me is going, don't forget there's only one value at each x value. Does this satisfy the 2 conditions I wanted to make it a probability function? Is this a PDF? Those are my 2 conditions. Does it satisfy both of them? Start with number 1. Is this function bigger than or equal to 0 for every x value? It's either equal to 0 or it's a quarter. That's bigger than 0. Yes, it satisfies number 1. What about number 2? Well, number 2 has me measure the area under this graph. I told you we're not going to do any calculus. The area under this graph,
Maybe it's the right side minus that one. So one.
well, that's my question. Is that area 1? But that area is a rectangle. It's got a horizontal top, a horizontal bottom, a left side and a right. That's a rectangle. What's the area of a rectangle? When those numbers are? The area of a rectangle. What are the A, what are the B that you mentioned, Felix?
Yeah, then it's B is the height.
So, height and width.
5 multiplied by 1.
Which is not equal to 1. That's equal to 0.25, isn't it? Oh, crud. So I did say I was going to cheat. We weren't going to do calculus. We didn't have to. We just have to do a little geometry in this case. Here's another function. What's the picture look like? Okay, algebra class was a long time ago. What is the graph y equals x? Felix?
No, it's not. F on X is X multiplied by and make sure to just put the right.
It's the same picture just with, I missed what you said at the end there.
I thought it's just X for, so it just basically says the same, but one is now 2. So the
Okay, so we're going to go out further.
yeah, one further and X's. So there's no defined value.
You're right, there's no defined value. This changes as we go from side to side, right? But the output value, the value we get out is the same as the value we put in, right? So when you put in 0, you get out 0. When you put in 1, you get out 1. When you put in 2, you get out 2. When you put in 3, you get out 0 because we've gone too far. But out here, it's 0. And back here, it's 0. But from here to here goes up. Whatever you put in, you get out the same thing. Again, I can ask this question. Is this a PDF? Will this work as a PDF. My same two conditions. Is this function bigger than or equal to 0 for all values of x? Yes. What's the area under this function? Almost. Because it's a triangle, right? It's half the rectangle, so base times height divided in half. So this time the area is 2, still not a PDF. Dang it. This time I did pick a fixed value. Since I picked a fixed value again, this is going to be another horizontal line. The height will be 1/6, but only between 0 and 6. Now it's PDF because this area, 6 times 1/6 is 1. And this is always bigger than or equal to 0. Hey, wait a second. What I'm saying in here is that the chance of any of these results occurring is 1 out of 6. But this isn't discrete. This is continuous. I could get the value 0.37. I could get the value 2.35. I could get the value 5.6728, right? I can get any value between 0 and 6. The chance is the same all the way across. There was a discrete version of this. What did we call the discrete version of this idea? This was Friday. We gave this a name. Same height all the way across. A uniform distribution. So what I've just created here is a continuous version of that uniform distribution. Okay, well, let's generalize. The continuous uniform distribution should be a function that's either 0 or some number. Now, when we were doing the continuous one, we could do it from whatever to whatever, right? I think we did ages. They went from 20 to 60. The age of a person at a computer firm. I've just forgotten the details of the problem. So I can go from any number to any number. Let's go from A to B. So I need a value for A to B, and then 0 everywhere else. I just need to know what number to put here to make this work. Well, the advantage is that I can use this example we have right up here. If I know I'm going from A to B, then my picture is going to start at A and end at B, and it's going to be some height. And it's going to be 0 everywhere else. The rectangle. How long is the base of this rectangle? Which means in order for the total area to be 1, the height needs to be 1 over B minus A. Huh. In other words, the entire uniform distribution can be figured out by knowing the two numbers. Where does it start? Where does it end? It goes from 13 to 125. Okay, 125 minus 13, 112. So the height must be 1 over 112. All I need are the two numbers. So we're actually going to call this function the uniform distribution from A to B. Those are the only two numbers I need. I could use this idea to build a formula for the CDF. Knowing that this is going to be the PDF picture means I know what the CDF picture is going to look like. The total area until we get to A, what's the total area? On this side, it's 0. And then by the time we've gotten to B, we've hit all the area, right? So I know this has a value of 0, and this has a value of 1. And the graph is a straight line. Which means I can use geometry and a little bit of algebra and I can figure out the equation of that line. It turns out the equation for this line is given by that. So that means that the probability of being less than or equal to x is exactly the value here. I really must tell you, I hate this formula. I don't use it all that often. I wanted to give it to you. It's in the textbook, the bottom of page 235. But I tend to think of this in the picture up there. I'm going to use this picture way more often to figure out what's going on here. An example. I have a uniformly distributed random variable, continuous variable, distributed from 25 to 45. Say to give me any number between 25 and 45. 29. So I have two different questions. What is the probability that I get a value less than or equal to 29? Now, my first reaction might be, oh, let me jump back to this formula right here. I'm not going to do that because I'm a geek. I'm not going to bother. I'm going to draw the picture. We go from 25 to 45, and we have some height. What is the height? What's my height? 1 over 20. Now, I'm asking, what is the chance I am less than or equal to 29? 29 is here, right? All I want to know is the shaded area. How long is the bottom of that box? And the height is 1 over 20. I'm done. Formula? What formula? I don't need a formula. I need base times height, damn it. This is a rectangle. Which you're welcome to write as 1/5 or 0.2 or whatever you want. Chris, give me a different number between 25 and 45. Okay, so now I could ask, what is the chance of being between 29 and 38? Again, that's not a CDF question. So I couldn't even use this formula if I wanted to. But what I can do is I can say 38 is going to be over here somewhere. So now I'm going to get this area. What's the base of that box? And the height is 1/20th. I am a really, really, really visual person when it comes to these functions. It's always a rectangle. That makes this really easy, in my opinion. I could use the CDF to answer this question. I could. Because what I could say is I could say, oh, this is really the chance of being less than or equal to 38. That would go from here all the way back to 25, minus the chance of being less than 29. So I'll take all of the shaded area and then I'll subtract this one. But since I'm taking all of the shaded area, that's a CDF question. So I could actually do that way. That's 38 minus 25 over 45 minus 25 minus 29 minus 25 over 45 minus 25. But notice this number is 4 over 20. And this number, 38 minus 25. And 13 minus 4 is 9. 9 over 20. Do I need the CDF formula? No. I just have to remember how to find the area of a box. And as long as I find the height of that box, I'm good to go. Hang on a second. There's something up in this stuff that I just wrote that bugs me, a very small amount. And being the geek that I am, I want to pick at this little nit and I want to split the hair here so you understand what's going on. If I say 29 less than or equal to x less than or equal to 38, I should include 29, right? This calculation says take everything less than or equal to 38. And then this calculation says take everything less than or equal to 29 and throw it out. Didn't I throw out 29? Technically, yes, I threw out 29. Why is this not going to be a problem? Because really what I should have used is this one, P of x strictly less than 29, and that would include 29. Here I threw out 29. But the difference between these two is just whether or not I use exactly the value 29. What is the chance we get exactly the value 29? 0. Remember, we said that right here, the chance of getting exactly a particular number is 0. So these two things are interchangeable. What we're really trying to say is that I'm going to measure up to the very edge of the rectangle, but I'm not going to include the very edge. I'm sorry, that was the BS detector going off. That's bullcrap. There's no area on the very edge. That's a length. So there's no area difference between these two. So that means, unlike what we were doing in the discrete case, I made a big deal about whether we used less than or equal to, greater than or equal to. In the continuous case, I don't care. That's true no matter what our distribution is. Whether I use an equal sign or not is irrelevant. Questions? The discrete uniform became the continuous uniform. My other discrete distribution was the binomial. So there's got to be a continuous version of that. But unfortunately, it gets a different name because it was discovered by a different person. The work of the Bernoullis in the binomial distribution was carried on by a guy by the name of Gauss, Carl Friedrich Gauss. And so the Gaussian distribution is the continuous version of the binomial. But almost nobody calls it a Gaussian. I know I just spent this time telling you the name. Why am I going to tell you not to call it that? Because we use this one so frequently. It's the picture I showed you earlier. It's called the normal distribution. And it looks like a bell curve. I'm a horrible artist. This picture is supposed to be symmetric. The same on the left as it is on the right. Around its center line, which will be the average. Wait a minute. This is continuous. I shouldn't use that symbol. For the average, I should use mu, the mean. I should use Greek for continuous stuff, population stuff. But there's one other piece of information I need to know to draw this picture properly. I need to know how wide to make this picture because I want the area under this thing to be 1. So depending on how tall versus wide it is, I could get a graph that looked like this or that looked like this. So the width is going to matter here. And the best part about this is that the width is the variance. And we know how to compute the variance. That's what variance means, is how far away from the mean do we get. We'll use the standard deviation to help me measure out. So in order for me to have a normal distribution, I need to be given a mean and a standard deviation. Just like I had to be given A and B to get the uniform one, I need to be given 2 numbers to get a normal one. So we're actually going to call this N mu sigma. The normal distribution whose mean and standard deviation are given. Now, most of the time, when I draw a bell curve picture, I'm just going to go ahead and put the mean in the middle, like this one. And then I think of the width as going off to the left and the right in terms of the standard deviation. This should look familiar. Where we added and subtracted standard. Okay, wait a minute. And then when we said you really only had to go out 3 in each direction, otherwise you were looking at outliers, right? And look at how small the values are once we get out beyond 3 in either direction. All right, wait, I had percentages, didn't I? There was that rule about this curve. The empirical rule for this shape said like 68% of the stuff should be between 1 standard deviation and then 95 point something and then 99.7. Those are measuring areas. If I go between this line and this line, that area should be 0.6826, 68.2%. And if I go out to here, that should be 0.954 something. And if I go all the way out to 3 on each side, that should be 0.997. But that means the area under this is 1. There's a formula. It's gross. It's disgusting. I will show it to you on Monday, and then we will forget it. Because I am not going to make you calculate the area under this curve. That's just gross, nasty calculus that will let the calculus people. However, this is the most commonly used distribution on the face of the planet in all of statistics. So from here on out, for the rest of the term, this is going to be your best friend. But we'll talk more about that on Monday. I hope you have a wonderful weekend. I will see you all then. If you came in late, come get your homework.